Okay, great. Thanks everyone for coming. So yeah, we're just going to talk a bit about our two zkEVMs, the Polygon 0 one and the Hermes zkEVM. And right now we're just talking about how we use Starks, but in these Starks, we really have multiple traces. And then we have a way to connect these traces together. So for example, I think we both have a trace for the CPU and a trace, for example, for Keccak. And then the CPU can sort of look at one of the rows in the Keccak table when it needs to check the result of a Keccak computation. So we have this sort of lookup argument between traces. And there's a few reasons for this. One reason is that if we did Keccak directly in the CPU, then like we would be in some sense we would be paying the cost of Keccak for every cycle in the CPU, even if we're not doing Keccak that cycle. We would still have to have columns in the CPU trace for all of the intermediate results of Keccak. And then we would need a way to disable the Keccak constraints if we're not doing Keccak. So it just seems to work better to have a table to have a separate table where every row we're doing Keccak, and it's really more specialized. It's more like having a coprocessor instead of having the CPU itself do like support some kind of Keccak instructions.
And there is another advantage that I think is important to mention of having a separate table, is that with the structure of the computation, it allows you to compute the proof much faster. So it's not the same if you have a specialized table that where you only do Keccaks, and then you can divide this table in chunks, and then you have a processor just computing Keccaks in that chunks. That works very well when you want to parallelize. If you have everything mixed in the single table, then this is a mess, and it's much more difficult. I mean, maybe you could do it, but it's much more difficult. So there is this low entropy of the system. You know, the system is much more Cartesian. You know, it's much more square, it's much more clear, and much more specialized. And this allows you to do higher, much better optimizations than if you are mixing everything in a single state machine. That's another important reason for having these specialized state machines.
Yeah, I think this is where a lot of projects are headed if they're not already doing, at least a lot of zkEVMs, if they're not already doing this, they probably will at some point, because there's a lot of efficiency reasons to do it this way. It also means, well, depending on how we do it, like in some versions, the tables can grow separately. So we can have, for example, in our Keccak table, we have this very wide arithmetization where we do a whole row of Keccak, a whole round of Keccak in one row. And the width of this trace is about 2,400 columns. So we wouldn't want the CPU table to be so wide. We want the CPU table to be very narrow because it's going to be long. There's one row for every cycle. But then just when we do a Keccak instruction, we can add this very wide row to this other table without affecting the shape of the CPU table.
And maybe just for explaining the Keccaks, because here we have different ways to approach the problem. So you went to a white, Stark. We bet with a very narrow Stark. Actually, we have we are just 3 columns for Keccaks. The difference is that we are computing 44 Keccaks at a time. So we have a very narrow. So we have like 150,000 columns. Okay. But then, so this is one catch. So one single Keccak is 150,000 columns, which is a lot. But actually, in this chunk, we are not doing one. We are doing 44 of them. So if you see the efficiency Altogether, we can do the numbers, but it's 100. So it's 150 divided by 44. This is about 2,000 or something like that. Okay, which is times 3. This is about 6,000. Which is, well, you are doing that with 2,000. So probably the way of doing with wider is like 3 times more efficient than the way that we are doing. Okay. So that's that. You can see here the relationship between going to white stars or long stars. Here, maybe you can see here. Maybe Daniel, you can explain, but looks like it's much more efficient going to wider stars in general.
Yeah, I think in general, wider starks mean we can have a witness with less redundancy because we never really pay for copying data to another row, or say doing like linear operations. We never pay for linear operations within one row. I think there is a bit of a trade-off that the wider starks increase verification costs and proof sizes potentially. If we go too wide, then it increases those things. But for us, we don't care too much because, well, we don't care about proof sizes because we just wrap these EVM proofs in a recursive proof, which shrinks the size effectively. And we care a little bit about verification costs because the higher the verification cost, the more expensive to create the recursive proof. But for us, the EVM proof is so expensive that even if the recursive proof is expensive, it's just not the bottleneck.
Yeah, exactly. The biggest bottleneck is in the main, in the EVM one, in the one that you have like thousands. In our case, is about 1,000 of polynomials. When you count everything together, the lookups and all the intermediate polynomials, it's about 1,000 polynomials. Well, yeah, you need to do the entities of 1,000 polynomials. You need to do the hashing, the mercantization of these polynomials with a Poseidon function. Well, this is much more expensive than doing. I think that the recursive, we can do it. Maybe you correct me because we do it a little bit different here, but it's less than, maybe it's like less than 1 million rows and 12 columns in our case. So then we can do a full recursion there. So it's just 2 orders of magnitude smaller. I think you in Plonky 2, I think this is even much more improved. So much, you go to wider and then you get even much better performance there. So
yeah,
the point and
go
ahead.
I was just
the point, and here is.
Sorry, go ahead.
Go, Daniel.
I was just going to ask if anyone had particular topics they'd like to cover, or else I had a couple of things we could go over. Okay, well, yeah, maybe we could talk about how we do arithmetic then. I think it's one of the bottlenecks in zkEVMs and something we've spent a fair bit of time thinking about, I think, for both of us. Does that sound good? Yeah, maybe I can share my screen here. Whiteboard. Okay. Just Okay, can you see that?
Yep.
Okay, so yeah, maybe I could just describe this idea that Jordi and I came up with together, and then I think it's a little bit different from what both of us actually implemented. So maybe after that we could talk about the actual implementations. But yeah, initially, so I think originally Jordi's idea was that maybe we could do arithmetic in a probabilistic way. So say we're just checking a multiplication, like x times y equals z, and these are 256-bit integers. So of course we can't really do this directly. We're working in a 64-bit field. So these numbers can't fit in our field. We have to use a bignum type encoding. So the original idea was maybe we can check it with under a random modulus. So we pick some random m and check that. And then maybe repeat this a few times, and then we get a probabilistic result that if this identity did not hold, then we probably would have detected it under one of these moduli. And then there's a variant of this that doesn't rely on randomness really, where we pick several moduli, we check this identity under each moduli, so actually now we're not picking random moduli. We're just beforehand we come up with some static set of moduli m, and then we check this identity under each each modulus, and after that we can infer that well, we know each modulus divides the difference, therefore the least common multiple of the moduli also divides the difference. Or in other words, this identity holds mod the least common multiple. And then from here, we just make an argument that basically this quantity can't be large enough to wrap around, because we have bounds on this quantity, right? We know there's n digits in some base. We know it can't possibly be larger than 256 bits, or no, 512 bits, actually. So as long as the LCM of our moduli set is more than 512 bits, then the only solution is the one with no wraparound. So then we can just infer that the identity holds. Does that make sense? And the key to the efficiency here is that we can do these checks very quickly, very cheaply, because really these are summations. Like each one of these quantities is a summation like this, because it's a bignum encoding. So there's several digits. Each digit has a weight, which is a power of our base b. And the key is that these powers of b are large, but they're static. We know them at preprocessing, and we also know the moduli at preprocessing. So we can partially reduce these quantities. Like this quantity becomes we just reduce the power of the base by our moduli, and we do that at preprocessing, so it doesn't really cost us anything. And then suddenly suddenly we're working with much smaller numbers. So in practice, this might, like, our moduli might be about 16 bits or 20 bits. And then when we multiply two of these quantities, we're still staying within the range of our field. So we can directly compute this without overflow. Yeah, I know I went a bit quickly. Are there any questions, or did that make sense?
What is the size of the set of moduli? I think it makes sense to me.
Okay. Yeah, good question. So we want, in this example, we want the LCM to be at least 512 bits. And then each individual modulus can't be too large, or else, because we need the property that, like, that we can directly compute this without overflowing our field. So that kind of limits the size of each modulus to about 20 bits. So the number of moduli we need is about 512 divided by 20. But there are some tricks we can use to make this better, to avoid needing too many moduli. So one trick we can use is we can use our native field P, our native prime P, as one of the moduli, and then checking this identity mod P is basically free because it's just native arithmetic in our arithmetic circuit. Another trick we can use, if we're doing modular arithmetic, or if we're, instead of, like, here I was using the example of a widening multiplication where Z could actually be 512 bits. But in practice, we're usually doing arithmetic mod 2 to the 256, or maybe mod the zkP base field order or something like that. And in those cases, what we can do is, well, maybe I shouldn't get into it, and I'd probably get it wrong right now, but there are some tricks in the paper that we can end up with much smaller bounds, and then for these types of operations, we end up only needing about 10 or 12 moduli.
Thank you.
Mm-hmm. And for each moduli, we're doing one range check. So yeah, it ends up being like 10 or 12 range checks basically, and each range check is about 40 bits with the parameters that we use in practice. Jordi, would you like to talk about how you do this?
Yeah, we are doing in the currency implementation. We are doing a little bit. We are doing a little bit different. So we are not doing probabilistic. What we are doing is, let me see if I'm able to explain. So the idea is that we, so imagine that you have 256 bits and 256 bits. So the first is we use chunks of 16 bits, very much like that. So we use 8 chunks of 8 chunks of 16 bits. 16 chunks of 16 bits. Okay, so we divide by that. We do a range check for each of these chunks. So this is a little bit costly, but it's we can do it in general. We're doing in 16 steps. So actually, it's just doing one check for in each. So one range check in each row. Okay, and then we do we do all the operations, and we are doing all the operations of multiplying y, but in the 16 bits and aggregating. So multiplying also for the for these constants all together, and this gives a result that in somehow this result needs to be 0 in the question. So, and then the idea is that, okay, the result, we have when we do the multiplication, if we extend, like we do multiplications, we go to chunks of 32 bits, okay? So we need to reduce these 32 bits to, again, to 16 bits back again. And then we do a technique of carry, of just taking the carry. So we are just reducing the first one to, so we have 32 numbers. So you just get the modulo 16. So you get the one that needs to be the units, okay? And then the others needs to be added to the decimals, okay? And then we do a range check of this carry. Okay, so then with this range check of the carry and the range check of the output, and then with this we guarantee that the result is 16 bits 16-bit padding, and just this requires a little bit more of range checks, but they are more. You know, at the end is I think in the arithmetic state machine we have like three range checks per row, and we have 16 rows. So it's this works. So it's quite optimal. And then you save here. So this back and forth is a simple state machine. Is just one step. You don't need this randomness and these things. And because it's very squared, it's very it's very easy, the implementation. You can see it in PIL. Then we can do this with just three. We can do that in just in 16 clocks and just three lookups or three range checks. Just three permutation checks. No, the three lookups. Actually, three columns of the three lookups we have. Okay, one for the range check, and one for the inputs, and the other for the output.
Would you say this is a bottleneck for your zkEVM?
Not now. So actually, the first bottleneck that we had was SketchUp. As I told you in the beginning, we were running. So this was the first bottleneck that we found in normal things. So, but we multiply it by 4. We went from 11 bits to 44 bits. So we are doing 44 bits in parallel. The next bottleneck that we found was the binary state machine, which is in binary we do additions, subtractions, comparations, these normal XOR, ANDs, all these things. This was the second one. We double it in this binary state machine. We do it byte to byte, and now we do it 2 bytes and 2 bytes. So make it a little bit wider, but it's much efficient. And currently, the limitation is in the processor itself. So it's in the clocks. Each program is a clock, and then this is the limit. So this is the first resource that it's getting out of resources is the clock. So we are where we supposed to be. Doing these optimizations and just removing these bottlenecks is where we go to. We went from a limit in the byte size of 4 millions to currently about 10 millions per byte size. And in arithmetization in normal transactions is not the limitation. Here the numbers is we are using actually it's not 16, it's 32 clocks. I say 16, but it's actually 32 because it's like when you multiply 16 chunks by 16 chunks, you get to a 32 chunks. So you have it's a 32 clocks. But 32 clocks, that means that you should do an arithmetic operation every 32 clocks, and we are doing an instruction, a film instruction in about 10 clocks. So that would mean that almost all the instructions should be a multiplication or a division, which is very difficult to reach this point. So this is not really the limitation. It's true that we are using, because this technique, we are talking about multiplications, but you can do any operation that just you can do, for example, an addition of various multiplications. We are using that, for example, for doing curve additions and curves you're doing for curve additions and core doublings for the ECDSA. We're using the same arithmetic state machine, and well, there you know, in each transaction we need to do like 512 operations of this kind for ECDSA. But this is well paid in Ethereum. You know, when every time you do an ECDSA, for example, for each transaction, you have 21,000 gas, and this is much more. In comparison, this is so you have a lot of gas to process this in comparison, for example, to with a mul operation that you just you need to do it in three gas. So it's not the arithmetic state machine currently is not. It's not the bottleneck, and it's difficult to be a bottleneck.
Mm.
Of course, it's what's a little bit the bottleneck is that it's one of there are a lot of polynomials, and you know, because this, when you are dividing with these 16 chunks, you know, it's 16 plus 16 plus the result. So it's like a lot. We have a lot of polynomials there. And then the carries so altogether the cost in the number of polynomials is similar to the main state machine. So it's a big it's one of the biggest state machines, but you need to have it anyway. So at the moment that you have it, you can you just use it.
Yeah, CPU is also one of the main bottlenecks for us. I think because it's a stack machine, there's so many rows where we're just doing something like a swap or a dupe, some kind of stack manipulation, and because of that, the CPU trace can be very long. For us, actually, the longest table is our memory table. So maybe for you it's together with the CPU table, but for us it's a separate table. And then we have kind of a 1 to 6, like each CPU row can do up to 6 memory operations. So we have this 1 to 6 lookup. And the memory table ends up being very long, but it's very narrow. So it's not a huge bottleneck.
Well, here is one of the differences that we have right now. We are currently working with fixed polynomial degree. That's why we more or less we adjusted. For example, in the ketchaks, we cannot go wider because we are limited to this. We need to be in the same degree of the polynomial. So what we did is the other way around. It's like you know, with this size, with this degree of the polynomial, how can we optimize the number of ketchaks that we can do there? Okay, so that's so we limit in our case we fix the degree size, and then we are just designing the state machine just to fit in these degree size, which this is not the most optimal way. So the most optimal way is it's what Daniel they start to do, what they are already doing, and we're thinking in really doing in the next versions. That's having these different degree in the state machines and then linking together. This is the other paper that is in the room. That's like when you have like when you want to do a permutation check between 2 state machines, one of degree, I don't know, 2 to the 25 and the other 2 to the 22. With this and with the recursion stars and all the technology, you can really have different state machines connected together with different sizes. And this is much more efficient because you are fully using, so you don't spend resources. So if in ketchak, for example, you can have this super wide ketchak, and which is much more optimal, and you can have like various versions, you know, a version with just 16 ketchaks, and you can have a version with 16,000 ketchaks. And of course, if you need to use 16,000 ketchaks, you can process, so you can use this huge state machine. Of course you need to spend, but you are doing 60,000 ketchaks. And probably if you are doing 16,000 ketchaks with the same amount of gas, maybe you are doing less, you're going to do less arithmetic operations, and then the arithmetic operations can be shorter. So the efficiency, the efficiency of the prover can be much more optimized with this technique, because you are not overspending. You are not overspending resources. You use all the resources that you are consuming, and that's much more efficient. Of course, this requires this proof with multiple domain, and just mixing the having common, like multiple proof, but with common challenges and doing these things. But this is perfectly doable, and it's much more efficient. And I think this is the way to go for really improving the efficiency of the provers.
Mm-hmm.
I don't know, Daniel, if you want to explain a little bit how this technique works of just using multiple domains.
Sure.
Cross domain lookup, cross domain permutation check actually.
Yeah, sounds good. I can explain. I think we're doing it almost the same way, but there might be some minor differences. So I'll explain our approach first. So say we have these two tables. We have the CPU table and let's say the catch-check table. And for each one, we have this a column, we usually call it Z, which stores a cumulative product of the data that we're connecting between these two tables. So at each row of the CPU table, if we're doing this column, this cumulative product starts at 1, of course, and then for each row, if we're doing a catch-check, then it gets multiplied by basically the catch-check input and output, which are compressed using randomness into a single value. Something like this. But then if we're not doing a catch-check, then it just stays as 1. It's just a cumulative product, which we only update on rows where we're actually doing catch-check. And then for the catch-check table, there's also this filter where we only update the cumulative product on certain rows, because the catch-check table does one round of catch-check in one row. So in other words, one whole catch-check permutation takes 24 rows. So only on that rows that are a multiple of 24, then we actually have the result that we want to pass back to the CPU table. It's the final output of the permutation. So similarly here, we start at 1, and then on certain rows, it gets multiplied by a randomly reduced input-output pair. And then at the end of it, then we just have these two Z last values, and we just assert that they're equal. That's just something the verifier does. It opens these final points of each cumulative product polynomial and checks that they have the same value. Is that similar to you, Jordi?
Yeah. Well, actually, we are not using strictly this, because we are just working in the same domain currently. But this is the way that we are. This is the way that we are planning to do it. And you just check the last one. You just the last one. It's important this concept of the selector. So what Daniel says, that which columns are you taking in account in that. Actually, for example, in the P language, we started with that in the P language. When you define a state machine, one of the parameters that you are putting is the degree of this state machine. So that's prepared to have like multi-degree state machine. The thing is that this needs to go farther, because it's not that you have different domain sites, it's that you need to compute a proof that accepts different domain sites. Okay, so and then here is where recursion plays an important role. So in the next step, it's like you have a verifier that accepts different proofs for different sites, but they share the same. The Z last, they share this last thing, and they share also this proof. They share the same randoms, because you need to compute it in a second phase, the same thing in both proofs. So it's a kind of cross. There are two proofs, but they are connected proofs somehow.
Yeah. Maybe we could just write it out what the constraint looks like. So there's a constraint which enforces that these cumulative products must be updated properly in this manner, where if we're actually doing a catch check, then there is no change. It just copies the previous value. If we are doing a catch check, then it multiplies the previous value by this random reduction of the catch check input and output. So I think in something like basic Plonk, we have a similar permutation check, and there's a constraint that looks like this, where this is the next value of the cumulative product. This is the previous value, and then actually in Plonk it looks like this. There's this quotient because we're sort of combining two cumulative products together. But for us, we can't do that combination because, as Jordi said, it doesn't work when we have tables of different sizes. Potentially, the CPU table might be a different size from the catch check table. So for us, it basically looks like this, except then we also need to incorporate the filter or selector, as Jordi says. So we don't always multiply by, this is some function representing the catch check input output. But we only multiply when the filter is on. So it looks something like this, which effectively what it's doing is using sort of Rust syntax.
Actually, there is a randomness here just to be safe, but yeah.
Yeah, true. Maybe I should write it like.
If you want to have the paper here, I can share maybe the formula. Maybe it would be. Yeah,
that's a good idea. Yeah,
let me share the screen.
Okay.
The formula is here. Okay. So here is in the first two equations, you are just checking that in the first row is 1 in both of them. This other one is the Lagrange one, so that means that when in the first row is 1 and the other is 0, that means that the ZF must be 1 at the first row. In the C and D, it's for each side of for the left and the right side. What we are doing this grand product, and here is we're multiplying by. So if the selector here, if the selector is 0, we are just multiplying the last one by 1, and if the selector is 1, we are just multiplying the last value of Z by the actual value. Okay, and we are in this gamma, which in order to be safe, because you don't really know what you are multiplying, but you are doing the same thing. This gamma needs to be the same in both columns. Okay, and in the last and the E and F, you need to check that actually they have exactly the same constant. It can be any constant, but must be the same in the left and in the left and in the right. And so these are the polynomial equations that you need to fill. Okay, so here is Okay, that's the thing. So it's like if G cell is 1, then that means that this must be fulfilled, but then this is subtracted, and yeah, you have it. You have it here. Okay, and also in you need to also this needs to go around. So in the last, so from going you need to exclude the cell1 and -1, you need to exclude the constraint from starting over again. So because you are accumulating, but you are not rounding up. So it's like you just finish there. So this is like the limit constraint that's added here.
Mm. Yeah, for us, it's basically the same, except that we for comparing the final values, we don't really do that as a constraint. We do it as more of a opening where the prover opens each final value and then the verifier manually compares them. But yeah, it's the same, effectively the same thing.
Yeah, there is a nice trick that you can explain. It's not relevant in cost, in the proving time cost, but it's interesting is especially for the fry that you can. So when you are folding, and you have like many proofs. The idea is that you have like different degrees, but then at some point you just join them together because you have a polynomial to a linear combination of the polynomials that you have at one of the stages of fry, and then you can continue just with a single folding. Just you don't need to do twice or 3 times. This is not relevant because in general the fry computation, the proving time is not relevant. It's really small compared to the proving time, but it's an interesting trick.
Yeah. I just noticed a couple questions in the chat. So Hector asked, what is the depth of the recursive proof? For us, it's about, if we're doing recursion where there's only a single inner proof, then we have 2 to the 12 rows to do that and 135 columns. And yeah, for us, it's a fixed circuit. We don't really support any kind of dynamic recursion where we can have a arbitrary size inner circuit. And then Wei asked, for ECDSA verification, 1 hash plus that many rows. Let me think about that. So I think ECDSA is 2 curve multiplications, right? And then, yeah, each curve multiplication would involve maybe 256 doubles and 256 adds. So I think in total we're doing a 1024 curve addition or doubles. Is that right?
I think it's double than that, but yeah.
Double. Okay.
In the worst case, this is an average, but in the worst case, I think it's 1,000 curve operation. Well, 1,000. It's 512 curve operations. Well, no, I need to check, but yeah, that is the worst case because when you have everything once, then you need to take the count in the worst case. So 256 bits, and then you do an addition and a multiplication, and you need to do that twice. So this is in total is 1,024 curve operations that are 2,000 arithmetic operations.
Mm-hmm.
And each of those translates to, each of those are non-native, right? So additional factor of 30.
Say that again.
Each one is 32, yeah. In our case, it's 32 clock. Well, but depending, but you can do it in a single row, because this is, you can do always, you can put also more polynomials than just less rows.
Mm-hmm.
Yeah, I'm just trying to figure out whether, so the factors were just 30 compared to like native, like tower curves. Doing the ECDSA will, non-natively will be like 30 times more constraints effectively. But it's not a bottleneck for zkEVM.
in our case, it's not the model. So what we have is not the bottleneck. I mean, you probably can do it with less polynomials. So at the end is how many polynomials does the arithmetic state machine, and we are also using some clocks in the CPU that this is consuming. Actually, this is the bottleneck. Is this because we are consuming some CPU clocks for doing all this logic? You know, it's the thing is that the CDSA is. There is a lot of logic there. You need to check that you are not, that's an addition, it's not a doubling, and that there are some, you know, that there is not zero or not negative number. You know, you need to do some. CDSA is not a freely snark. It's not a freely circuit thing to do. It works well when you have a processor, okay. And what we're using is okay. We already have a processor. Okay, let's use this processor in order to do this logic for the CDSA, and then let's use the arithmetic state machine that we already needed for the zkEVM, because we need to do 256 mixed multiplication, so we need to do other things just to do also this operation. So we are, in somehow we are having this CDSA for free. It's not really for free, okay? But we would need it if we didn't have this CDSA. We would need it anyway, an arithmetic state machine, and we need a processor. So actually, the real cost is the clocks that we are taking from the processor. We could put this clock in a specific state machine just to do these things, okay? And then we will have the other end. Then here we come the numbers that Daniel come up. But you know, in our case, this is a trade-off here. For the recursion, we are doing a little bit worse than them. The truth is that the Plonky 2 is the recursion part. It's very, you know, it's very. They squeeze to the limit, to the, you know, to the optimization on that point. We are a little bit worse, but I would say it's enough. Actually, we are working with for a recursion of two proofs. So it's a recursion. So we need to actually it's an aggregation more than a recursion. It's an aggregation. So we are proving two proof of the same proof. Okay, so it's like double. We are using. I don't want to lie here. I think this is 2 to the 19, but only 12 columns. Okay, and which is it's 90 to 2 to the 20. But it's 1 million columns 2 to 12. It's in any case, it's much. It's in. I mean, it's significant, but it's much less than the main state, than the main. zkEVM state machine. So for us, this works very. They were good enough, but again, we can do it much better. And here the example is the Plonky 2. Its numbers are impressive.
Thinking about ECDSA, for us, it's also not really a bottleneck. But I think if we were to really optimize it, it could be quite cheap. For example, using that technique that we described here, we described just doing it for multiplication, but really we can generalize it to any low degree identity and if it's still a quadratic identity, then nothing changes very much. The range checks might just become a tiny bit larger depending on how many terms we have. So we could take the curve equations, and I think if we compute the slope separately, then we end up with 3 identities that are all quadratic. And then we could even use randomness to combine those into a single quadratic identity. And then it's almost the same cost as checking one multiplication to do the whole curve operation. So then it's like a few hundred bits of range checks to do one curve operation. So we haven't done that yet because it doesn't seem to be a bottleneck so far, but I think it's possible to make it very, very fast.
So in our case, we do the trick of this splitting having like one equation with many fields. We have the prime number, and so we have at the end we have three equations, one for addition, one for doubling, and another for the slope. the slope calculation, and but we are not doing this random, this non-deterministic approach. We're just doing the operations and that's it, and we are not combining them together, and that's interesting. That's a cool idea.
So what will be the factor of savings here? So like one curve operation is usually like about 10 underlying field operations. So is it basically saving instead of doing this multiplication or addition 10 times, effectively we're batching this to almost like complexity of one multiplication, as you said. So it's like a factor of 10 improvement potentially.
Yeah, I think so.
Okay.
Also for us, we don't really, I'd have to double check. I think we're just doing a widening multiplication and then a reduction. We're not really doing anything that's like specialized to the modulus of the zkP base field. So yeah, there's a lot of potential optimizations that we haven't done so far.
Would the cube in the curve for zkP be a problem?
What cube? What is that?
I guess like for checking data points on the curve.
You just do two multiplications.
Okay.
Here in this technique that we explain it, in general, we are working with quadratic, things that, you have quadratic expressions. But I think it should be easily extensible to cubic equations. This may have sense for some operations. Here we are planning, for example, to use this technique for implementing pairings. We need to implement pairings because there is a precompiled smart contract in Ethereum that it's doing the BN128 pairings. And for doing pairings, we can use exactly the same techniques, but instead using the BN128 curve operation. So this is the idea of implementing pairings. We have the arithmetic already still machine, so it's just a matter of defining these new these equations that are required for pairings, and what is an exercise to do. That's just getting what are the right equations. How you optimize pairings for zk for a zk circuit. That's that's a little bit tricky because for example, divisions that are very expensive in normal computation, they are very cheap. For example, in constraints somehow. So we need to redo all the maths, all the formulation of the pairings, just taking into account these new parameters for optimization. That's definitively possible. We did some exercises, and for example, I don't want to lie because it was a hackathon that we did that, but I think I think it was like 2 to the 22 multiplications or something doing a pairing in the BLS curve in that case. So we expect a little bit less in the BN curve. But yeah, that's the kind of operations. But if we are optimizing, this was just doing normal additions and multiplications, not doing these specialized, specific equations for that. So I think that we can reduce at least 2x or 4x just with these equations at least. So it's but this is a pending work. It's a to-do work that's in the list to do. We are focusing in the launching the mainnet right now. So this will be the next step.
Are there any questions before we wrap up? Okay, well, thanks everyone for coming.
Okay, thank you very much.
Thank you. Bye-bye.
Thanks, Daniel and Jordi.
Bye-bye.